Good afternoon, everyone. This is Kimia Tasnia. I am going to present the summary of paper. So I will be presenting 4 papers. So here is my first paper, functional verification of DSP based on board VLSI designs. This paper is about making it much easier to verify complex DSP blocks that sit on board in space or embedded systems. Think of big FFT cores or sine cosine lookup tables. They are mathematically heavy, highly optimized, and often implemented in fixed point. Writing a full bit accurate checker in System Verilog for each of those is painful, slow, and very easy to get wrong. The author's big idea is, instead of reinventing all the math in the test bench, use MATLAB, the tool DSP engineers already trust as the golden reference. So the verification environment is built in System Verilog or UVM like usual. You have constant random stimulus driving the DUT, monitors collecting outputs, and a scoreboard deciding pass or fail. The twist is inside the scoreboard. When a transaction comes in, the scoreboard calls out through a DPIC wrapper into MATLAB, passes the same inputs the DUT saw, and asks MATLAB to compute the correct result using its built-in FFT or sine cosine functions, including fixed point conversation. The MATLAB result comes back through the C layer, gets compared to the DUT output, and any mismatches are flagged. They demonstrate this on 2 real space-borne IPs. For the 8192.FFT, overlaying the DOT spectrum with MATLAB's reveal subtle precision and register length effects that would be hard to spot otherwise. For the sine cos LUT, they can literally sweep all 2 to the power 16 possible input angles and verify that every 10-bit fixed point output matches MATLAB. The takeaway you can emphasize is that this flow reuses trusted MATLAB models, reduces the effort to build checkers, and gives much better visibility into DSP behavior, while still fitting cleanly into a standard UVM verification environment. The next paper is the system verification methodology for advanced TLM verification. This paper is about bringing UVM-style verification into the system TLM world. The System C is great for early transaction level models, but it doesn't natively support strong constraint random and coverage driven verification. Existing libraries like OVM-SC and SCV only cover parts of that, so people end up with ad hoc test benches that aren't as rigorous as what we do at RTL with UVM. The authors propose SVM, the System Verification Methodology, a UVM-like library for System C. It gives you familiar components, test, agent, drivers, monitors, sequencers, sequences, and plugs in a System C coverage. Plus, crave for powerful constraint random generation. They demonstrate it on a virtual self-balancing EV platform. An SVM test creates an agent around the TLM DUT. The sequences generates constraint random steering and speed comments. The driver sends TLM transactions, and the monitor and subscriber collect coverage on comment types and sequence patterns. The key point is that SVM plus Crave can handle complex comment sequence constraints that SCV struggles, with enabling true coverage-driven constraint random verification directly at the TLM level much earlier in the flow. The next paper is QMC, which is a formal model checking verification framework for superconducting logic. This is a paper from 2021, a recent one. This paper brings formal verification to superconducting SFQ logic, which behaves very differently from CMOS. Signals or pulses gates are inherently clogged, and designs must obey strict fan-out and path balancing rules. Those quirks break many assumptions in standard verification flows, and existing semi-formal tools like VeriSFQ don't scale well. The authors introduce QMC, a model checking framework tailored to SFQ, starting from a BLIF netlist. QMC runs structural checks for fan-out and path balancing, then automatically generates SFQ-style Verilog, a system Verilog wrapped with formal assertions and configuration files for open-source engines like USYS, SMTBMC, or EBMC. The model checkers then either prove these functional and timing properties or produce counterexample waveforms when they fail. On benchmarks such as Coke-Stone adders, multipliers, and dividers, QMC finds both functional and structural bugs and can be up to about 20 times faster than VerySFQ. The main takeaway is QMC turns SFQ verification into an automated open source formal flow instead of relying on slow ad hoc semi-formal methods. The final paper is application of error detection and correction techniques to self-checking VLSI systems. This paper is a survey-style overview of how error detection and correction techniques are used to build self-checking VLSI systems, especially as technologies scale down and soft errors become more frequent. The basic problem is that smaller feature sizes and lower voltages make circuits much more vulnerable to transient faults, which is unacceptable in safety critical domains like aerospace, automotive, and medical. Designers therefore need mechanisms that can detect and sometimes correct errors during normal operation without relying only on external testing. The authors walk through the main classes of fault tolerance strategies, fault avoidance versus fault tolerance, and then focus on concurrent error detection using coding techniques. They compare common codes such as parity, Hamming, Berger, and residue codes in terms of fault coverage and area overhead. The key takeaway is that residue codes, and in particular Module 3 residue coding, often give the best trade-off for data path circuits. You compute a residue on the inputs, compute a residue on the outputs, and compare them. Any mismatch flags an error. The survey reports that traditional codes like parity or Hamming can add around 47 to 54% redundant area, whereas residue codes can get similar or better detection with about 40% overhead. And a real RISC-I CPU example shows only 23.6% total area increase for residue-based checking. That's impressive. Overall, you can get roughly 99.8% area detection with significantly less area than full duplication, making residue codes a very attractive building block for self-checking VLSI. Now, if we want to look into the overall trends of the four papers, you can see a common story. Verification and reliability are getting more automated, more rigorous, and more domain specific. The DSP paper shows how we can plug MATLAB directly into a UVM testbench and reuse trusted DSP models as golden references instead of hand coding complex math in System Verilog. The SVM paper does something similar at a high level of abstraction. It brings UVM-style components, constraint random generation, and functional coverage into pure system CTLM. So we can do coverage-driven verification much earlier in the design flow. The QMC work moves from simulation into full formal on the other hand. It tailors model checking to superconducting SFQ logic with the right structural checks and temporal properties, and then leverages open source engines like USYS and EBMC to either prove these properties or give counterexamples. Finally, the self-checking VLSI paper looks at the infield side of the problem. Instead of just finding bugs before tape-out, it surveys on-chip error detection schemes and highlights residue codes as a way to get near duplication level fault coverage with much less area. So the similarities are all for are trying to close gaps in existing flows. They all rely on some form of reference behavior or properties. meta functions. TLM platform behavior, SFQ assertions, residue invariants, and they all aim to boost confidence without exploding cost. Now, the main difference are in technique and timing, I would say. Simulation plus coverage versus formal model checking versus hardware error detection and pre-silicon design verification versus post-silicon runtime fault detection. Together, they span a continuum from better test benches to better formal proofs to better self-checking hardware. Thank you so much for joining. Have a great day.